If n squared is odd, then n is odd. So this is in, especially in our class and the classes like in real analysis, most of the time, if you have an if-then, if you have an implication, then that is our theorem. So most of the theorems are results that we use in mathematics that we have to prove are in the if-then form in our in these elementary textbooks. Okay, so at this point, this is pretty, it's pretty concrete. We know the idea of odd as far as generalizations is. What's the most general thing here or abstract in this theorem here?
N.
N, very good. So let's define, let's make N concrete. Now we are pretty good. So when is this thing false? When is this thing true? If N is replaced with 1 or 3 or 5 or 6, this statement is true. If N is replaced with 2, 4, 6, this statement becomes false. So this thing here can be false or true given depending on what N is.
Okay, so we have N is odd, N squared is odd. So these are our two statements.
These are two different. So here we have N. Again, what is N? 1, 2, 3. And then you square. If you square 1, you get 1. And this statement is still true. So let's actually do that. So we have 1 is odd. So this is true. 2 squared is even. So is not odd. So this is false. So it works for 1, doesn't work for 2. 3 squared is 9. 9 is odd. So for certain values of n, this statement works. For certain values of n, this statement is false. Same thing here. Okay, all right. So now, as it's stated, it's pretty concrete right now, especially since I made sure we know what n was, right? So if I took this out, we are now increasing the generalization. N could be integers now, right? It could be natural numbers, integers, even fractions, maybe. Fractions of the type where in the denominator you just have 1, right? Okay, so let's do what we came here to do. Now I want to increase. I want to increase the abstraction. Abstraction. So I'm going to replace this thing with a letter P. And N is odd. I'm going to replace it with Q. Okay, so what's happened now is that we can call these two things statement. This is a statement. And a statement can be true or false, true or false. So usually what happens is, so remember I was saying this is a theorem for us, we have to prove is, so what happens is this bit here, the P is usually the given as in taken, assumed to be true. So we usually assume this to be true. We assume the P to be true. And if we assume that is true, then we have to see that if we assume this to be true, then is this also true or not? So this is given, we assume this to be true, and this we have to check whether it is true or false. Okay, so if you're given an implication, this is called the antecedent, and this is called the consequent. And in order to prove this implication, in order to prove this, that this implies this, when do we prove that? This implies this when we say, we assume this is true. If we assume the antecedent to be true, then does it imply the consequent or not? So this is the step here. When we assume the antecedent P to be true, when we assume the antecedent P to be true, then we are in a position to check whether P implies Q. If we assume P to be true, does that imply that Q is also true? Q is also true. Okay. Okay. So we're given the implication if P, then Q, and we have to write a proof. At this stage, and we're doing a direct proof.
Oh, we're not doing proof by contradiction?
No, we're doing a direct proof. And in a direct proof, what do? We assume the antecedent, the P to be true, and at that, and when we start the proof, we don't know if this is true or not. So the initial conditions are, so let's call this theorem. The initial conditions. This thing here is assumed true. And at this stage, what we have to do is we have to prove the implication. The implication itself is true or not. And then here, this is up for grabs, whether it's true or false. So the initial condition is we assume this to be true, assume true, and then at this point, we don't know. We don't know that if we assume this to be true, this will be true as well. And what we want is, we want two T's. We want a T here and a T here. Okay, all right. There's one other thing. So I'm going to rewrite that again. So if it's blue, if the statement P is assumed to be true, then, so if the statement P is assumed to be true, then is it the case that the statement Q is also true? Okay, so let me back up, and I've been messing up. This is the initial condition. This is when you see an implication, the implication is saying this. This is what the implication is saying. When you see an implication, it's saying that we have assumed the P to be true and Q is also true. What we have to check is if this is true or not by doing the proof.
Yeah, so the proof is the question.
So at this point, this is actually still, yeah, a question. This is the assumption that we make.
Yep.
But when you see an implication, this is what it's stating, and we just need to check this. Check this. And how do we check this? So check this. We check it by doing assume this to be true, assume true, and then Q, and then we have to check if Q is true or not. We assume P to be true, and then we check if we assume P to be true, will Q be true or false? But the implication itself says this implication is true if this thing is true already. Okay, all right. So we're not going to go into the truth table today, but mainly
this truth table is
this right there. We want two T's. We want the truth here and truth here.
Yep.
Because if it was false here and false here, the implication is still true. We don't care about that. We don't care for the trivial cases. In the theorems, we always want this guy to be true. Or, okay? All right. So another way to deal with this is, so sometimes it's actually easier to prove the contrapositive of this thing. Okay, so this is our implication. So this is the original implication. And then the contrapositive. of this thing is if not Q all right, and then again, so what do we do here? We assume this to be true. This implication is this whole implication is going to be true if P and Q are both true. So when we do the proof, we assume P to be true, and then we check to see if Q is true or not. If it is true, then the implication is true. Over here, it turns out it's easier if we deal with the negation of the statements. And so then in this case, we will assume this to be true and see if this is true, it implies that this is also true. If we assume this to be true, this is also true, because that's still up in the air. And if it is true, then this whole implication is true. Okay. And then the third method of is the proof by contradiction. So this is, you could call that, if this is contrapositive, we prove the what we're doing here is we use as is, right? So this is, we'll prove this theorem as is. We take this and prove this. If that doesn't work, we take the contrapositive of this and prove this. The third way is to restate the theorem as to generate a contradiction. We're going to restate this guy to generate a contradiction in the proof. So we're going to do this. If P, then not Q.
Could you also, if not P, then Q?
We did that. So not Q, not P, and then we only do that. This is always not, this is the same.
Okay.
So and then what happens is if you're doing this one, we start here and we try to derive from P something that looks like Q.
Yep.
Okay. We derive from this something that looks like this statement. Right? Then over here in the contrapositive, we start here and try to derive something like that. If we are successful, we have our proof works. And over here, where do we start in the contradiction?
Start at not Q.
This is assumed true. Exactly. Start here. Start here. And as we are deducing stuff from not Q, as we are deducing and manipulating and expanding, as we are expanding the not Q, at a certain stage, we can bring what is assumed into the game. So at a certain stage, this will come in. we start here, we get there. We start here, we get there. We start here, and at a certain stage, we bring this in because this is assumed true. No, not, yeah, this is also assumed true. So in the proof by contradiction, we assume this to be true, and we assume this to be true, and see if we run into trouble or not.
Yeah, so then if this statement holds,
Yeah, then that means that the original theorem was wrong. If this statement does not hold and we run into a contradiction, then our negating the Q was a bad idea.
all right,
Okay, all
Mhm.
right. That does look good, huh?
that looks really good. I
Yeah.
was gonna ask if you could leave that up for just a second.
You had a question?
I'm just gonna write it down in a more concise form.
Okay. All
So
right.
as is the first one.
Let's just call it original. So these are formulations of the same implication as in theorem.
And then we're running to the contrapositive. Finally, contradiction.
Might be my best picture.
I like the iPad because it has all the fancy colors.
Yeah, and then you can also quickly erase and add something and fix things up.
It has an undo button. You don't
Hmm.
even have to erase. You just spam the undo button.
Yeah,
if
I
you
do
go back
that,
far
yeah.
enough.
Yeah. So there's GoodNotes and then also OneNote by Microsoft.
Yeah, I did a lot of research on what Note app to get.
Yeah,
and
okay.
everybody was
So
like,
Notability,
Notability is
that's
what
the big one
works.
right now. Oh,
It's like it's a subscription. It's like $20 a year, but
it's better than all.
it links with iCloud, so all my files are in iCloud, and then
Hmm.
you have all of this. I could just like grab everything here.
Right,
you
yeah,
know.
yeah. Undo that. You
Yeah.
know how to do that. Good. Okay. So this is the concrete version. This is the generalized version. These two are identical. Here we would have if n is even,
Mhm.
negate that. If n is even, then n square is
Not odd.
or is even.
Yeah, is even.
Yeah.
Yeah, because you could do not odds or
Yeah,
even.
yeah. And then over here, n squared is odd. That's our assumption.
Yeah.
And here, n is even. So we have n is even, n squared is odd. We start with n is even, and we go and we mess with it. We expand, we try to make deductions from it. And then at a certain stage, bring in something we need to bring this in. When we bring this in, a contradiction happens, usually. Or we'll see, so that's how it works. Okay, so to do a proof by contradiction, we take the original implication and negate the conclusion or consequent. We still assume the antecedent, the statement P to be true. This is still assumed true. We don't start here. We start with the conclusion. We start deriving statements from the conclusion. And at a certain point, when it is relevant, we bring P in. And when we bring P in and no contradiction happens, then this reformulation of the original theorem is the correct theorem. When we bring the P in and we run into a contradiction, that means this reformulation of the original theorem was incorrect, and this is the way to go. And because the contradiction happens, therefore we have shown this is true.